Hello everyone, welcome back to lecture series. Myself, Dr. G. Venkat Navachandra, Assistant Professor at SR University, working in the Department of Civil Engineering. Today we will discuss about the trickling filter, rotating biological conductor, and stabilization pods. So first of all, we need to discuss about the trickling filters. So see, this is the pictorial view of trickling filter. So this is the attached growth process. So in previous lecture we discussed about the active sludge process, that is the suspended growth process. So here microorganisms will be attached to the particular media so that whatever the wastewater flows on the reactors, microorganisms will sit one place and eat the organic matter. So that's why it is called as attached growth process where microorganisms grow on packing media. Wastewater is distributed over media, so biofilm degrades organic matter. So air supply oxygen for biological activity. Slugging means excess biofilm detached and it is washed away. So the whatever the bacteria it will attach to the media. When thickness will be increased, what will happen is automatically detached from the media, so that is called as slugging. So effluent plus slug solids are collected and sent to the secondary settling tank. Here also this is the first unit and followed by there will be secondary clarifier. So what is the working procedure? So wastewater is distributed over non-submerged packing materials. So the wastewater generally flows over the non-submerged packing materials. Air circulation supplies oxygen to the microorganisms. Means generally microorganisms require oxygen. That's why we are providing some kind of air circulation. So and microorganisms form an attached biofilm on media surface. As we discussed, the microorganisms growth will be happen on the media surface. Then organic matter is metabolized by, by biomass into the new cells. So biofilm thickness increases with the continuous treatment. When wastewater flows, what will happen? So whatever the organic matter present in the wastewater, it will be degraded by microorganisms. So if it is microorganism degrading, that means the growth also will be increased. So growth will be increases. So whatever the attached to the media, the thickness also will be increases. That particular time it will be detached from the media. So here is oxygen penetration limits. So what will happen if thickness will be increases? Oxygen penetration also is not possible. That will be converted to the anaerobic. So inner microbes enter into endogenous phase. Here it means inside there will be no oxygen. So endogenous phase means what are the bacteria? If they require food, what they will do? So they will eat particular bacteria. So that is called as endogenous phase. So excess, what are the excess biofilm detached due to the loss of adhesion. That is called as slugging. So here inner microbes enter endogenous phase means they will kill themselves and take it as a food. That is called as endogenous phase. Then excess biofilm detached due to the loss of adhesion. So the sluggish solids and treated water are collected through the underdrain. The collected effluent is sent to the secondary settling tank for the separation. So these are the types of filters. See, types of trickling filter. One will be the low rate filter, high rate filter. Low rate means here is the low organic loading, no recirculation, high nitrification. So high rate filter means higher organic loading rate, uses recirculation and partial nitrification. So these are the two types of trickling filters. Then what are the key design parameters? So one will be the hydraulic loading rate. Then second important thing, the organic loading rate, that is the BOD based. Then what will be the filter depth and what are the media we are using. then what will be the recycling ratio? For suppose you are using the high rate filter, so we need to go for the recycling ratio. So if we are using the low rate filter, there is no recirculation. So here is the performance. It is a BOD removal efficiency is around 75 to 90 percentage. So in ASB we discussed around 85 to 90 percentage. So compared to ASB, the performance will be reduced here. Then suitable for domestic and industrial wastewater. So these are the means some kind of trickling filter design to calculate the efficiency of particular trickling filter. So two equations have taken from the literature. These are the empirical equations. One is the NRC equation, then second one with the Rankes equation. So, means how to calculate the efficiency. These are the empirical equations. So that means what are the units, their particular parameters we need to strictly follow. See, E means percentage of BOD removal equal to 100 divided by 1 plus 0.44 square root of F into BOD. F into BOD means BOD loading rate. That should be substitute as kg per day. Then V means filter volume, that should be substitute as meter cube, not in liter. We need to, if question liters is provided, we need to convert into the meter cube. Then RF will be the recirculation factor. So next equation will be Rankes equation. What is a Rankes equation? Generally, this equation used for high rate filters. Here E equal to R by Q plus 1. R means we know R by Q means recyclation ratio. E means BOD removal efficiency. So next slide will be the problem, design problem. See, read the question properly. A trickling filter receives 5,000 meter cube day of wastewater with influent BOD of 200 milligram per liter. The filter volume will be 1000 meter cube and recirculation factor will be RF equal to 1. Estimate the BOD removal efficiency using the NRC equation. Here, which equation? NRC equation. So, so first of all, F into BOD should be in kg per day. So those parameters given in the previous equation. So we need to convert these units into kg per day. So here food means here wastewater flow, that is 5,000 meter cube per day. So next one will be the BOD. BOD will be the 200 milligram per liter. So the unit should be in kg. That's why we are converting to kg per liter. So it is 0.2 equal to, it is around getting 1000 kg per day. Then equation should be efficiency equal to 100 divided by 1 plus 0.44 by equal to F into BOD will be the 1000 divided by, so what is the 1000 here? Volume multiply with the recirculation factor RF equal to 1. Everything will be substituted. So here finally the efficiency will be 69.4 percentage. So the BOD removal is around 69 percentage. So what is the next secondary unit will be rotating biological contactors. So secondary treatment using RBC are kind of rotating plastic discs. That is the fixed film. The microorganisms in the farm is the formation of biofilm and media. So rotation alternates exposure to wastewater and oxygen. Say about 40% immersion ensure the aerobic conditions. Organic matter degraded by attached biomass. Excess biomass is removed by slugging and followed by clarifier. So these are the components: media disk, shaft, drive system, reactor basin, cover. So what is the operation? So rotation speed is around maintaining 1.5 rpm. Maintain oxygen transfer to the inside water. Then uniform rotation prevents imbalance. So this is the typical diagram of RBC, that is a rotating biological contactor. So this is the rotating disc. So what is flows through this rotating disc? So what will happen? So means biofilm being formed at the rotating disc, then water also flows. It is also kind of attached growth process. Then after some time we need to send to the secondary clarifier. Then after that is the affiliate. So what is the RBC media and the rotation? So biofilm grows on the media with the microorganisms for the treatment. Similar to the trickling filter we discussed, the biofilm thickness should be 1 by 16 to 1 by 8 inch. Then media should be kind of not react with the microorganisms. That's why we are choosing the plastic disc with the spacing and corrugations for better flow and surface area. So rotation of media. Disc rotate alternatively through the wastewater and air. Shaft plus media together form the drum. Rotation speed we are maintaining 1.5 rpm. About 40% of media is submerged at a time. Ensure oxygen supply and effective treatment will be happened. So coming to the next biological treatment or secondary treatment will be the stabilization of ponds. So here the stabilization of ponds are open flow through the basins, specifically designed and constructed to treat sewage and biodegradable industrial waste. They provide long detection periods extending from a few to several days. So this pond system in which oxygen is provided through the mechanical aeration rather than a algal photosynthesis are called as aerated lagoons. So lightly loaded ponds used as a tertiary step in wastewater facility, polishing of secondary effluent and removal of bacteria called as maturization ponds. So here stabilization of pond is divided into three types. So one will be the aerobic ponds. So aerobic ponds are shallow ponds and with a depth less than 0.5 meters, and BOD loading rate will be 40 to 120 kg hectare per day. So as the maximize the penetration of light through the liquid depth, such ponds develop intense algal growth. So coming to the anaerobic ponds, are used to pre-treatment of high-strength waste with a BOD load of 400 to 3000 kg hectare per day. Such ponds are constructed with a depth of 2.5 to 5 meters as light penetration is unimportant. So higher anaerobic conditions we are maintaining. In previous class we are maintaining the aerobic condition. That's why in previous case depth will be less, here depth will be high. So next one is the facultative pond functions aerobically at the surface while anaerobic conditions prevail at the bottom. So here basically facultative pond means on the top layer it will be act as the aerobic and bottom layer will be acted as the anaerobic conditions. These are the three different types of stabilization ponds. So what is the mechanism of purification? How it will be happened and how it can be remove the BOD. So first of all, functioning of facultative stabilization pond. Here, sea-based organic matter is stabilized through the both aerobic and anaerobic conditions. So here the The entire zone we are dividing into the two zones. One is the top, one will be the aerobic layer, and the bottom will be considered as the anaerobic layer. So coming to the aerobic layer, oxygen is supplied mainly through the algal photosynthesis. We are not providing any external oxygen to the plant. So it will be circulated and it will be created oxygen through the algae photosynthesis. So non-settlable and dissolved organic matter here will be oxidized. The organic matter, firstly, it will be converted into the carbon dioxide and water. The products of partially anaerobic decomposition that rise to the surface are also oxidized. So next layer or bottom layer will be the anaerobic layer. Generally, it contains settled sludge from the raw wastewater solids and microbial biomass from aerobic process. What are the means oxidation will be happen at the top layer. It try to go down at the bottom. So first one will be the solids. Next one will be the microbial biomass. Then the organic matter undergoes anaerobic decompositions. So what will happen if it is undergoes anaerobic conditions? Then first product will be formed will be the methane. There itself in aerobic condition it will form carbon dioxide and water. Then methane escapes from the fan in the form of gas bubbles. The what is the symbiotic relationship in the pond? We are not providing aeration to the pond, but still the organic matter degraded by aerobic bacteria. So what kind of means mechanisms going on? So algae produce oxygen through the photosynthesis. What will happen during the photosynthesis? Algae will be releases oxygen. Then bacteria is required oxygen to degrade the organic matter. So, if means during the degradation process, so what will happen? Bacteria will release CO2, so which will be utilized by the algae. So algae can take the CO2 from the bacteria, then it will be utilized, and during this process, oxygen will be released. That oxygen will be utilized by bacteria. This is kind of a cycle. So this creates a mutual relationship between algae and bacteria. That is called as symbiotic relationship in the pond. So this is the pictorial view of symbiotic relationship. So this is the raw wastewater. So raw wastewater we are sending to the facultative pond. Here top layer will be the aerobic, the bottom layer will be the anaerobic. So during the photosynthesis formation of new cells, so what will happen? Algae will be released the oxygen. So oxygen can be utilized by the bacteria during the formation of new cells or growth. Then bacteria will be releases carbon dioxide. Then carbon dioxide can be utilized by the this algae. This is called a symbiotic relationship. Then what will be the final output will be the then effluent, then algae, then bacteria cells in the aerobic conditions. So anaerobic conditions we know. So whatever the means degraded in the aerobic condition, it gets settled on the bottom. Here ultimately it will be their organics. That organics will be converted to organic acids, and this is the means kind of end products at the anaerobic condition will be CO2, ammonia, and methane. The methane will be escaped as the water bubbles. So this is the one of the important design in the aspect of environmental engineering. So how to design the lagoons? So lagoons or ponds are both are means same only. So you see here this is the kind of pond. Then initially the flow rate will be Q. Then initial BOD concentration will be S naught. Then after treatment the means the flow rate will be somewhat QE or SC. So as per facultative fund here is mentioned top layer the aerobic anaerobic layer. Then after applying the mass balance equation on the lagoon. So this is the final equation. S by S naught equal to 1 by 1 plus k into V by Q equal to 1 by k into theta. So here S by S naught will be the fraction of soluble BOD remaining. K will be the reaction rate constant day inverse. Theta will be the hydraulic detection time, that will be the day inverse. Then V equal to reactor volume, that should be substituted as the meter cube. The flow rate also meter cube per day. So this is the for single reactor. If several reactors are arranged in a series, the effluent of one point becomes the influent to the next. So if the concentration of BOD is more, then one reactor can't handle the strength of BOD. So we need to go for the series of reactor. Here, after one reactor, whatever the effluent coming from the this particular reactor, that will be the influent from the next reactor. That is called as Lagrange series design. So the equation after deriving the equation could be SI divided by S naught equal to 1 by 1 plus k theta by n whole to the power n. This is the equation used to calculate when the means lagoons or ponds in the cities. So temperature is one of the major important factor here. So temperature coefficient or temperature constant needs to be calculated for the particular temperature. So here is the reaction rate constant at 20 degrees centigrade will be taken as the constant, and if temperature is given maybe 35 or 45, we need to calculate. K20 value they will give as per the constant, and the pi value also they will provide. Then if you know what kind of reaction rate constant for particular temperature needs to be calculated, that also needs to be substituted here. We will get particular K30. If you want, you can calculate K40 also, K10 also, we will calculate. So that pi value is a range of 1.03 to 1.12. Here is means one design problem. This is means very important problem. So see, the wastewater flow from a small community averages 3,400 meter cube per day. So in winter, this is the volume. In 6,600 meter cube per day during the summer, the average temperature of the coldest month will be 10 degrees centigrade. Means in winter, the temperature will be is given as 10 degrees centigrade. For that, we need to design a reactor for 10 degrees centigrade, and the average temperature of the warmest month will be 30 degrees centigrade. Means here in summer, the average temperature will be 30 degrees centigrade. The average BOD is 200 milligram per liter with 70% being solid. Then reaction rate coefficient K equal to 0.23 day inverse at 20 degrees centigrade. I mentioned K20 value always they given in the question. So here is the, and the temperature coefficient will be is around 1.06, 1.06, as we mentioned the range 1.03 to 1.12. Then prepare a preliminary design for a faculty pond treatment system to remove 90% of soluble BOD. So find the volume of facultative lagoon. Find the dimensions of three square lagoons in series, each having a depth of 1.5 meters. So I think question is very clearly given. So the BOD, effluent BOD will be 90% of soluble BOD means, so here, so 90% is removed means the effluent BOD will be 20 milligram per liter. So I will show the answer step by step. See, first of all, we need to calculate the temperature constant or reaction constant. So K20 value means we know the uh, reaction rate constant. We will calculate the based on this equation. This equation already written in a previous slide. So it's very simple. This is the equation. So summer that average temperature will be 25. It is mentioned in the question. So K25 equal to K20 value is given as the 0.23 day inverse. Pi value is given 1.06. Then T in place of T we need to substitute as the 30 degrees. There here it is 25, not 25. It is a K30 we are calculating. Then next, this is for summer. Then winter, what would be the average temperature? K10. The substitute 10 minus 20. It is getting a 0.128 day inverse. Next, we need to calculate the volume of login. If it is 1, then what could be the volume of the reactor or volume of the pond? See, S by S naught equal to 1 by 1 plus K into theta. Theta here means theta. How to calculate the hydraulic retention time? Theta equal to volume divided by flow rate. So, here is the effluent BOD. How to calculate? So it is required to design a 90 percentage BOD removal. BOD removal. Initially BOD, how much? Initially BOD will be 200 milligram per liter. See here, how much? 90 percentage removal means the effluent will be the 20 only. So 20 divided by 200 equal to 1 by 1 plus 1 plus here summa that K value should be 0.411 divided by V by that summer flow rate will be 6600. Then volume we are getting around 1,44,525 meter cube. This is for the summer. We need to calculate for winter also. So same equation, only one is changing. That is the K value. K value here 0.411. Here K value will be the 0.128, and flow rate also will be changed. Here 6,600. Here 3,400. The volume here we are getting around 2,39,062 meter cube. So when you design a reactor, that should be useful for any season. That's why we are calculating the extremes in summer as well as the winter. If someone asks you to calculate the uh, means volume of particular reactor or pond, it should be 2,39,000 meter cube. Why? So if you are designing a 2,39,000 meter cube reactor or pond, what will happen? During the means high flow rate, it can sustain. During the less flow rate, also it can be work. But if you are designing volume 1,45,000, so what will happen during the winter time? There will be means not sufficient place to accommodate the waste what is coming from the community. So next will be the estimation of dimensions of three square logules. See here the logules will be in the series. So that is a V1, V2, V3. So all are should be in a square size then equal dimensions. So here the equation will be Sn divided by S naught equal to 1 by 1 plus k into V by n into q whole to the power n. So here this 1 by means here we can go for S naught by Sn, then this will becomes upside. So 1 plus then summer we know the constant value, then we need to calculate n means series it should be 3. Here is the float in summer will be 6,600. The volume will be around 55,000 meter cube. In winter also we need to calculate K value will be vary, Q value will vary. It is around 91,980 meter cube. So in the worst scenario, what will be the volume login will be taken? So here is the maximum will be the 91,980 cubic meters. So here depth in the question is given as 1.5 meter for every lagoon. So this means area could be 91,980 divided by 1.5 will gives the 61,000 meter square. So it is in a square size, that means square root of 61,320.53 will gives the 247 meter square length and 247 meter square as the width. Then depth is given as in the question 1.5 meters. So this is the means problem regarding the facultative point. So thank you very much. Next lecture I will discuss about the tertiary treatment.